There is a force woven into the fabric of space itself, one that has no source, no location, and no explanation that fully satisfies. It cannot be seen, touched, or measured directly. It does not interact with light. It leaves no visible trace across the landscape of the cosmos. And yet, it dominates the universe. It accounts for roughly 68% of everything that exists, and its influence reaches across every corner of space, working quietly and without interruption, pushing the largest structures in the cosmos steadily apart. This is dark energy. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and contemplation. If you are settling in for sleep or study, find a comfortable position and allow yourself to relax. There is no rush here. The universe has been expanding for nearly 14 billion years, and it will continue long after tonight. We have plenty of time. Tonight, we are going to explore what dark energy is, how astronomers came to know it exists, and what it tells us about the nature of space and the long-term future of everything. We will move through these ideas slowly and carefully, giving each one the space it needs to settle. We will begin with the expanding universe and trace the path that led scientists to one of the most unexpected discoveries in the history of modern physics. We will look at the evidence, the theories, and the many things that still remain genuinely unknown. And we will end, as this subject naturally invites us to end, with quiet reflection on what it means to live inside a universe whose largest ingredient we do not yet understand. We will also touch on how dark energy relates to dark matter, why Einstein's most famous mistake turned out not to be a mistake at all, and what some of the most ambitious scientific instruments ever built are currently trying to learn about this invisible pressure that fills all of space. Each of these threads connects back to the central question, the question that has shaped cosmology for the past 3 decades. What is dark energy, and why is the universe accelerating? Before we can understand dark energy, we need to understand the universe it inhabits. And the most important thing to understand about the universe is that it is not sitting still. For most of human history, the night sky was treated as a fixed backdrop. The stars moved across the heavens in their nightly arc, following patterns that ancient astronomers mapped with extraordinary precision. But the positions of the stars relative to one another appeared constant. The cosmos seemed, on the larger scales, to be stable and unchanging. This was not simply a casual assumption. It was a deeply held philosophical commitment. A universe that simply existed in a steady and eternal state felt more fitting than one in motion. That picture began to change in the early 20th century, slowly at first, and then with remarkable speed. The tools available to astronomers improved, new instruments were built, and the ability to study faint and distant objects grew considerably. What emerged from that improved view was something no one had quite prepared for. In the 1920s, astronomers began to notice something unusual about certain faint, smudged objects in the sky. These objects had been catalogued for decades under various names, often referred to as nebulae, meaning clouds. Some of them had a spiral shape, some were more elliptical. For a long time, there was genuine disagreement about what they were. Were they relatively nearby clouds of gas within our own galaxy? Or were they something else entirely? Objects so distant that their true scale was simply beyond the limits of earlier instruments. The debate was settled in a decisive way by an American astronomer named Edwin Hubble. Working at the Mount Wilson Observatory in California in the early 1920s, Hubble was able to identify individual stars within some of these spiral nebulae, specifically a type of pulsating star known as a Cepheid variable. Cepheid variables are enormously useful to astronomers because they brighten and dim in a regular cycle, and the length of that cycle is directly related to how luminous the star actually is. By measuring the cycle and comparing it to the star's apparent brightness as seen from Earth, an astronomer can calculate how far away the star must be. What Hubble found was startling. The Cepheid variables he identified were not nearby at all. They were at distances so vast that the spiral nebulae containing them could not possibly be part of our own galaxy. They were separate galaxies entirely, enormous collections of hundreds of billions of stars, lying at distances measured not in light years, but in millions of light years. The universe was far larger than anyone had imagined. This discovery alone would have been enough to reshape astronomy for a generation. But Hubble did not stop there. He continued observing galaxies and recording their spectra, the way light from each galaxy is stretched or compressed, depending on whether that galaxy is moving toward or away from US. What he found, published in a landmark paper in 1929, was that nearly every galaxy he observed had its light shifted toward the red end of the spectrum. This redshift indicated that almost all galaxies were moving away from our own. More than that, there was a pattern. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, pointed toward a single extraordinary conclusion. The universe was expanding, not expanding from some central point outward, like an explosion from a fixed location, but expanding in the sense that the space between galaxies was stretching. Every galaxy was moving away from every other galaxy, not because the galaxies themselves were flying through space, but because the fabric of space between them was growing. This distinction is worth sitting with for a moment. When we say the universe is expanding, we do not mean that galaxies are rushing outward through empty space towards some outer boundary. There is no boundary, and there is no center of expansion. What is expanding is space itself. The distance between objects is increasing because the medium they occupy is stretching, like dots drawn on the surface of a balloon that is slowly being inflated. Each dot moves away from every other dot, not because the dots are moving, but because the surface between them is growing. This picture of an expanding universe was not immediately accepted. It required significant adjustment to the prevailing models of cosmology. Even Albert Einstein, whose equations of general relativity had already predicted a dynamic universe, had initially resisted the idea by introducing a term into his equations, specifically designed to keep the universe static. When Hubble's observations made the expansion undeniable, Einstein reportedly called that intervention the greatest mistake of his scientific career. We will return to that term, the cosmological constant, in a later chapter, because it turned out to be far more important than Einstein realized. For now, the key point is this. By the middle of the 20th century, astronomers had established beyond reasonable doubt that the universe is expanding. Galaxies are moving apart. Space is stretching. And this expansion traces back, if you follow it in reverse, to a moment roughly 13.8 billion years ago, when everything we can observe was compressed into an extraordinarily small and dense state. That origin point is what we call the Big Bang. Though the name somewhat misrepresents the reality, it was not an explosion in space. It was the beginning of space itself. With an expanding universe established as the foundation, a natural question followed. What would happen to that expansion over time? The answer that most physicists and cosmologists assumed for several decades seemed almost obvious. Gravity would slow it down. The logic was straightforward. The universe contains an enormous amount of matter. All of that matter exerts gravitational attraction on all other matter. Gravity pulls things together. If the universe is expanding, gravity should be working against that expansion, gradually decelerating it, the way a ball thrown upward gradually slows under the pull of Earth's gravity. The question was not whether the expansion was slowing, but how much matter the universe contained and whether there was enough to eventually reverse the expansion altogether, bringing everything back together in a final contraction. This was the theoretical landscape in the 1990s when a new generation of astronomers set out to measure with high precision exactly how much the expansion had been slowing over time. What they found would change everything. In the mid-1990s, two independent teams of astronomers set out to do something that had never quite been achieved before. They wanted to measure the deceleration of the universe's expansion with enough precision to determine its ultimate fate. Both teams were using the same tool for this measurement, a particular kind of exploding star known as a Type 1, a supernova. These stellar explosions are among the most luminous events in the universe, bright enough to be seen across distances of billions of light years. And crucially, they have a property that makes them extraordinarily useful as measuring instruments. We will look at the details of why in the next chapter. For now, the important thing is that astronomers had developed confidence that Type 1 a supernovae could serve as reliable distance markers, allowing measurements of cosmic distances with a precision that had not previously been possible. One team was led by Saul Perlmutter at Lawrence Berkeley National Laboratory, working under the banner of the Supernova Cosmology project. The other team, led by Brian Schmidt and Adam Rees, operated under the name the High Z Supernova Search Team. The two groups worked independently, used different approaches to data analysis, and did not share results until both were ready to publish. This independence was deliberate. A discovery of this magnitude would need to be confirmed by separate lines of evidence. Both teams spent years collecting observations of distant supernovae, painstakingly measuring their brightness and comparing that brightness to what would be expected at various distances in a universe whose expansion was slowing down. The analysis was careful and methodical. There was no reason going in to expect anything other than confirmation of deceleration. What they found instead was deeply unsettling, at least at first. The distant supernovae were dimmer than expected. Not dramatically dimmer, but measurably so, in a way that was consistent across many observations and could not easily be explained away as measurement error. In the framework they were working within, dimmer meant farther away, and farther away than expected, given their redshifts, meant the universe had expanded more than it should have if gravity had been steadily decelerating things. The expansion was not slowing down, it was speeding up. Both teams arrived at this conclusion independently. Both were initially cautious about it. The result was so contrary to expectation that the natural response was to look for errors, to check and recheck the data, to consider alternative explanations. Perhaps the distant supernovae were being dimmed by dust. Perhaps they were intrinsically different from nearby supernovae in ways that had not been accounted for. Each potential source of error was examined carefully. None of them could account for what had been observed. By 1998, both teams published their results. The universe's expansion was accelerating. Something was causing it to speed up rather than slow down. That something had no name yet, no theoretical framework that fully explained it, and no clear physical interpretation. But the evidence was there, and it was consistent, and it pointed in only one direction. The cosmological community absorbed this result with a mixture of fascination and unease. It was not simply that the result was unexpected. It was that it required something new, something that did not fit neatly into the existing picture of what the universe contained. If gravity pulled things together and the expansion was accelerating anyway, then there had to be some other component of the universe whose influence worked in the opposite direction, something that drove expansion rather than resisting it. This unknown component was given a name: dark energy. The name was chosen partly by analogy with dark matter, which had already been established as an invisible and undetected form of mass, and partly to reflect the fact that this new component appeared to be a form of energy associated with space itself. The name stuck, even though it describes something we do not yet understand, and even though the word energy carries connotations from everyday life that may not fully apply here. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for this discovery. The citation noted the significance of finding that the expansion of the universe is accelerating and the role this played in establishing dark energy as a fundamental feature of the cosmos. It was one of the more remarkable Nobel Prizes in the history of the award, recognizing a discovery that had deepened the mystery of the universe rather than solving one. The accelerating expansion has since been confirmed by multiple independent lines of evidence. It is not in doubt. What remains in doubt, and what remains one of the deepest unsolved problems in all of science, is what dark energy actually is. We know it exists in the sense that its effects are measurable and consistent. We know roughly how much of it there is. We know something about how it behaves, but we do not know what it is made of, why it has the value it does, or whether it will remain constant forever. Those questions will occupy much of the rest of this exploration. But before we go further into theory, it is worth spending some time with the instrument that made the discovery possible, because understanding how a Type 1a supernova works as a cosmic measuring tool helps illuminate how confident we can be in the underlying observations. The story of how astronomers came to trust Type 1a supernovae as measuring instruments is itself a story of careful, painstaking science. It begins with a problem that has always been central to observational astronomy. How do you measure the distance to something you cannot reach? On Earth, distance measurement is relatively straightforward. You can use a ruler, a tape measure, a laser rangefinder, or radar. For nearby objects in space, there are methods that work reasonably well. Parallax, for instance, exploits the fact that a nearby star appears to shift its position slightly against the backdrop of more distant stars when viewed from opposite sides of Earth's orbit. By measuring that shift, and knowing the diameter of Earth's orbit, the distance to the nearby star can be calculated with geometry. This works well for stars within a few thousand light years, but for objects at cosmological distances, objects billions of light years away, parallax is far too small to measure. Astronomers need a different approach, and the most reliable approach involves what are called standard candles. A standard candle is any object whose intrinsic luminosity, meaning how bright it actually is, rather than how bright it appears from Earth, is known. If you know how bright something truly is, you can compare that to how bright it appears in the sky, and from the difference calculate how far away it must be. The principle is the same as knowing that a particular street light has a certain wattage and using its apparent brightness to estimate how far down the road it is. The challenge is finding objects in space that reliably have the same intrinsic brightness. Stars vary enormously. Most objects in the universe do not have a consistent, predictable luminosity. Type 1a supernovae are exceptional in this regard. though the reason for their consistency took some time to fully understand. A Type 1a supernova occurs in a binary star system, a system where two stars orbit each other. One of the stars in the pair is a white dwarf, a dense stellar remnant left behind when a star like our Sun exhausts its nuclear fuel and sheds its outer layers. A white dwarf is supported against gravitational collapse by a quantum mechanical effect called electron degeneracy pressure, and it has a maximum mass it can sustain this way. That maximum, known as the Chandrasekhar limit, is approximately 1.4 times the mass of the Sun. In the binary system, the white dwarf can accumulate material from its companion star over time. As it does, its mass gradually increases. When the mass approaches the Chandrasekhar limit, the white dwarf can no longer support itself. The carbon and oxygen at its core begin to undergo runaway nuclear fusion. Within seconds, the entire white dwarf is consumed in a thermonuclear explosion of extraordinary energy. This is the Type 1a supernova. Because the explosion always occurs at approximately the same mass, the energy released is approximately the same each time. This means the intrinsic brightness of a Type 1 supernova is approximately the same, regardless of where in the universe it occurs. An astronomer observing a Type 1a supernova in a distant galaxy can use its apparent brightness to calculate how far away that galaxy must be, with a confidence that is not available for most other objects. There are refinements to this picture. Type 1. A supernovae are not perfectly identical. They vary somewhat in brightness, and astronomers have developed techniques to correct for this variation. It turns out that the way a supernova brightens and then fades over time is related to its peak luminosity. Brighter supernovae tend to fade more slowly, and by measuring the light curve, the shape of the brightness over time, astronomers can standardize each supernova to a common reference brightness. This correction, developed in large part by the Chilean astronomer Mario Hamui and later refined by others, was essential to making Type 1a supernova the precise cosmological tools they became. With standardized Type 1a supernova in hand, the two teams in the late 1990s could do something genuinely powerful. They could observe supernovae at different distances, meaning different points in the universe's history, since light from distant objects takes time to reach us and therefore shows us those objects as they were in the past. By comparing the distances inferred from the supernova's brightness to the distances inferred from their redshifts, they could map how the universe's expansion rate had changed over time. It is worth taking a moment to appreciate what this means. When astronomers look at a supernova 10 billion light-years away, they are seeing an explosion that occurred 10 billion years ago. The light from that explosion has been traveling through expanding space for 10 billion years before reaching our telescopes. By comparing the brightness of that ancient explosion to what would be expected in various cosmological models, astronomers can effectively read the expansion history of the universe directly from observations. What that history showed was a universe that had been decelerating in its early phases, as gravity acted on the dense matter of the young cosmos, and then, at some point roughly 5 to 6 billion years ago, had transitioned to acceleration. Something had changed. The balance between gravity pulling things together and whatever was driving the expansion apart had shifted. Gravity had been winning for the first half of the universe's history, and then something else had taken over. That something is what we call dark energy. And to understand it more deeply, we need to return to a concept from the history of physics, one that was introduced, discarded, and then quietly vindicated over the course of a century. To understand dark energy in its most widely accepted form, we need to spend some time with a single symbol from the history of physics. That symbol is the Greek letter lambda, and it has had one of the more unusual careers in the history of scientific ideas. It was introduced as a solution to a problem, dismissed as an error, and then quietly restored by observational evidence nearly a century after it was first written down. The story begins with Albert Einstein and his theory of general relativity, published in 1915. General relativity is a theory of gravity, but it is much more than that. It describes gravity not as a force in the traditional sense, but as a consequence of the curvature of space-time. Mass and energy curve the fabric of space-time around them, and other objects follow the curves created by that curvature. What we experience as the pull of gravity is, in this framework, simply the natural path that objects follow through curved space-time. When Einstein applied his equations to the universe as a whole, he found something that troubled him. The equations did not produce a static universe. They predicted a universe that was either expanding or contracting. Given the assumptions of the time, a universe in motion seemed wrong. The prevailing view, held not just by Einstein, but by most physicists and astronomers of the era, was that the universe was eternal and unchanging on the largest scales. A cosmos that was expanding or collapsing did not fit the picture. To fix this problem, Einstein introduced an additional term into his equations. This term, which he represented with the symbol lambda, acted as a kind of built-in repulsive pressure that could counterbalance gravity and hold the universe in a steady state. It was not derived from any physical observation or any deeper theoretical principle. It was added specifically to produce the result Einstein wanted, a stable static universe. For a time, this appeared to work mathematically, but there were problems. The static universe that lambda produced was not truly stable. It was in a state of unstable equilibrium, like a pencil balanced on its tip. Any small disturbance would cause it to either expand or collapse. This was an uncomfortable property for a model meant to represent an eternal and unchanging cosmos. Then came Hubble's observations. When the evidence for an expanding universe became undeniable in the late 1920s, the motivation for the cosmological constant evaporated. If the universe was expanding, there was no need for a repulsive term to hold it still. Einstein reportedly abandoned the cosmological constant with considerable frustration, describing his introduction of it as the greatest blunder of his career. For several decades, lambda largely disappeared from cosmological discussions. It was treated as an artifact of a wrong assumption, a mathematical patch that had served no real purpose. And there things stood for roughly 60 years. The cosmological constant was not entirely forgotten. Occasional papers explored its theoretical implications, but it was not considered a serious part of the standard cosmological model. The universe was expanding, gravity was presumably slowing that expansion, and lambda seemed unnecessary. Then came 1998 and the supernova results. When the accelerating expansion was confirmed, theorists immediately began looking for explanations. What could cause the expansion to speed up rather than slow down? The most natural candidate, and in many ways the simplest, was the cosmological constant itself. If lambda represented a real physical property of space, a kind of energy inherent to empty space itself, then it would behave in exactly the way needed to explain the observations. Here is the key insight. In general relativity, energy causes space-time to curve, and different kinds of energy curve it differently. Ordinary matter and radiation cause space-time to curve in ways that decelerate expansion. But a cosmological constant, and energy associated with space itself would have the opposite effect. As space expands, the density of ordinary matter decreases because the same amount of matter is spread over a larger volume. But the energy density of the cosmological constant does not decrease. It remains the same everywhere, in every cubic meter of space, regardless of how much space there is. This property means that as the universe expands, the cosmological constant's influence grows relative to the influence of matter. Eventually, it dominates, and when it dominates, it drives accelerated expansion. This is precisely what the observations show. For the first several billion years of the universe's history, matter was dense enough that gravity dominated and the expansion decelerated. Over time, as the universe expanded and matter became more spread out, the cosmological constant's influence grew in relative importance. Roughly 5 to 6 billion years ago, the balance tipped. The cosmological constant began to win, and expansion began to accelerate. We are living in that accelerating phase now. So the cosmological constant, Einstein's supposed greatest blunder, turns out to describe the dominant form of energy in the universe. The value Einstein assigned to lambda was chosen to balance gravity and produce a static universe, which was the wrong value. But the concept itself, the idea that empty space carries energy, appears to be correct. The universe does contain something that behaves like a cosmological constant, even if we do not yet fully understand what it is. This interpretation, in which dark energy is simply the energy of the vacuum of space, is called the cosmological constant model, and it is currently the simplest explanation that fits all available observations. It is the foundation of what cosmologists call the lambda CDM model, where lambda refers to the cosmological constant representing dark energy, and CDM stands for cold dark matter. This model, sometimes described as the standard model of cosmology, is not complete and not without its tensions and unresolved questions. But it remains the framework that best organizes what we currently know. What does it mean for empty space to have energy? This is a question that touches on both cosmology and quantum mechanics, and it does not have a clean, satisfying answer. In quantum field theory, the branch of physics that describes particles and forces at the smallest scales, empty space is not truly empty. It is filled with quantum fields, and those fields have a baseline energy even in their lowest possible state. This baseline energy is called vacuum energy, and it is a genuine prediction of quantum mechanics. The existence of vacuum energy has been confirmed through various laboratory experiments. It is real. The problem is that when physicists calculate how large the vacuum energy should be, based on the principles of quantum field theory, they get an answer that is vastly larger than what we observe as the cosmological constant. Not slightly larger, enormously larger, by a factor that is sometimes estimated as 10 raised to the power of 120. This is the largest discrepancy between a theoretical prediction and an observation in the history of physics, and it is one of the deepest unsolved problems in all of science. We will return to it in a later chapter, because it deserves careful attention. For now, the important takeaway is this. The cosmological constant provides a mathematically clean description of dark energy that fits the observations well. It represents a form of energy uniformly distributed throughout space, with a constant density that does not change as the universe expands. Whether that description corresponds to vacuum energy, to something else entirely, or to a property of space-time we have not yet understood, remains an open question. The symbol lambda describes the behavior. It does not explain the cause. Tim vienaz ar vien comats nulle secunde. Sleeps vitra lilax par. One of the things that makes dark energy genuinely difficult to grasp is that it does not seem to do anything in the world we can directly observe. Galaxies orbit within their clusters. Stars orbit within galaxies. Planets orbit their stars. The solar system behaves exactly as Newton and Einstein predicted. Gravity governs everything at the scales we interact with. Dark energy appears to play no role whatsoever in any of this, and yet it dominates the universe. To understand how this is possible, we need to think carefully about the relationship between scale and force. Different influences in the universe operate at different scales, and what dominates at one scale may be completely irrelevant at another. This is not a strange or unusual feature of physics. It is a recurring pattern. Consider gravity itself. On the scale of everyday human life, gravity is the background condition of existence. It keeps us on the ground, holds the atmosphere in place, and governs the motion of water and falling objects. But at the scale of atoms and subatomic particles, gravity is so weak compared to the electromagnetic force and the nuclear forces that it plays essentially no role at all. The gravitational attraction between two protons is negligibly small compared to the other forces acting between them. Physics at the atomic scale operates as if gravity did not exist, because for practical purposes at that scale, it does not matter. Dark energy is the reverse of this. At small scales, on the scale of atoms, planets, solar systems, galaxies, and even galaxy clusters, dark energy is utterly negligible. Its effect on the orbit of Earth around the Sun is immeasurably small. Its influence on the structure of a galaxy is far too weak to measure directly. Gravity, and in some contexts electromagnetism and the nuclear forces, govern everything at these scales. Dark energy simply does not register. But at the scale of the universe as a whole, across distances of hundreds of millions and billions of light years, the picture reverses. At these scales, matter becomes vanishingly sparse. The average density of matter across the entire observable universe is extraordinarily low, roughly equivalent to a handful of hydrogen atoms per cubic meter of space. At this level of dilution, gravity's influence across the cosmos as a whole becomes very weak, and dark energy, which is uniform and pervasive and does not dilute as space expands, becomes the dominant influence. This is why dark energy overpowers gravity on cosmological scales without doing anything noticeable on smaller scales. It is not that dark energy is stronger than gravity in any absolute sense. It is that dark energy is evenly spread across all of space at a constant density, while matter becomes more and more dilute as the universe expands. The balance between them shifts over time as expansion proceeds. Let us think about this more concretely by considering what happened over the history of the universe. In the very early universe, shortly after the Big Bang, matter and radiation were packed into an extraordinarily small volume. The density of matter was immense. Gravity was powerful. Dark energy was present, but its influence was trivial compared to the gravitational pull of the dense, hot, early cosmos. The expansion that had begun with the Big Bang was decelerating, exactly as you would expect when gravity is the dominant force. As the universe expanded, matter spread out. The density of matter decreased with the growing volume of space. Radiation became even more dilute than matter, because the expansion also stretched the wavelengths of photons, reducing their energy. But the density of dark energy, if it behaves as a cosmological constant, stayed the same. Every cubic meter of space contains the same amount of dark energy regardless of how large the total volume of space becomes. For several billion years, matter was still dense enough that gravity dominated. The expansion continued but decelerated. Then, roughly 5 to 6 billion years ago, when the universe was approximately half its current age, the density of matter had fallen enough that dark energy's constant density began to matter in relative terms. The two influences reached a rough balance, and then dark energy began to win. The deceleration reversed. Expansion began to accelerate. Galaxies that had been moving apart began moving apart faster. This transition was not sudden or dramatic. It was a gradual shift, like the turning of a tide. The universe did not notice any particular moment. Galaxies did not suddenly lurch apart. The change in the expansion rate unfolded over billions of years, and its detection required instruments sensitive enough to measure small differences in the brightness of supernovae across cosmic time. It is also worth being precise about what accelerating expansion means for individual structures in the universe. Galaxies, galaxy clusters, and the larger structures, bound by gravity, are not being torn apart by dark energy. Within a gravitationally bound system, gravity holds things together, and dark energy's influence at those scales is too weak to overcome it. The Milky Way is not expanding. The solar system is not expanding. Earth is not expanding. Dark energy's effect operates only at the larger scales, where the structures are not gravitationally bound, and where the distances are large enough for the uniform pressure of dark energy to manifest as a measurable acceleration. A useful way to think about this is to imagine two boats on the surface of a river. If the boats are tied together, the current of the river does not pull them apart. The rope holds them. But two boats that are not tied together, separated by a large distance, will be carried apart by the current in a way that no rope connects. Dark energy is like that current. Gravitationally bound systems are like the tied boats. The vast spaces between galaxy clusters, where nothing is gravitationally bound across those distances, are where dark energy's influence is felt. What determines when dark energy wins? The answer lies in the relative densities of dark energy and matter at any given time. In the early universe, matter density dominated. As the universe expanded, matter density fell, while dark energy density remained constant. The crossover point, where dark energy began to dominate, occurred at a redshift of approximately 0.3, corresponding to a time roughly 9 billion years after the Big Bang. Before that point, the universe was matter-dominated and decelerating. After that point, it became dark energy-dominated and accelerating. We are now several billion years into the dark energy-dominated era. The expansion is accelerating, and unless dark energy changes in ways we have not yet detected, that acceleration will continue indefinitely. The implications of this for the long-term future of the universe are profound, and we will explore them in detail in a later chapter. For now, it is enough to hold this picture. A universe where gravity shaped everything for its first half, and where an invisible, uniform energy now governs the larger scales of the second half. We have now established that the universe contains dark energy, that dark energy dominates on the larger scales, and that it is causing the expansion to accelerate. But it is worth stepping back at this point and considering the universe's total contents more carefully, because dark energy does not exist in isolation. It is one of three major components that make up everything the universe contains, and the relationships between those three components shape the cosmos we observe. Cosmologists often describe the universe's contents in terms of an energy budget, a way of accounting for everything the universe is made of and expressing each component as a fraction of the total. This budget is derived from multiple lines of observational evidence, including the detailed structure of the cosmic microwave background, the distribution of galaxies across large scales, and the supernova measurements we have already discussed. The numbers are well constrained, even if the nature of the components is not fully understood. The three main components are ordinary matter, dark matter, and dark energy. Ordinary matter, the kind that makes up stars, planets, gas clouds, dust, and everything we can see and touch and detect directly, accounts for approximately 5% of the total energy content of the universe. Just 5%. Everything that has ever been observed through a telescope, every atom that has ever been catalogued, every element in the periodic table, every galaxy whose light has reached us, all of it together constitutes a small minority of what the universe contains. Dark matter makes up approximately 27%. Dark matter is not the subject of this video, and we explored it in depth in the previous episode of this series. But as a brief reminder, dark matter is a form of matter that does not interact with light and cannot be seen directly. Its existence is inferred from its gravitational effects on visible matter, including the rotation of galaxies and the bending of light around massive structures. It clusters and clumps under gravity, forming the invisible scaffolding within which galaxies form and evolve. It is real, its gravitational effects are well measured, and its nature remains unknown. Dark energy accounts for the remaining 68%. More than 2/3 of everything in the universe is this invisible, uniformly distributed form of energy that we detected only because it is causing the expansion of the universe to accelerate. We cannot see it, cannot detect it in any laboratory, cannot point to a single direct observation of it. We know it is there only because of what it does to the universe as a whole. It is worth pausing to let that sink in. The matter that makes up everything we have ever directly observed, every star, every planet, every gas cloud, every living thing, all of it together is just 5% of the total contents of the universe. The other 95% consists of two things we do not understand: dark matter and dark energy. The universe, in this sense, is mostly unknown to us. We are like someone who has carefully catalogued every fish in a pond without realizing that the pond itself, the water, the substrate, the chemical environment, makes up the overwhelming majority of what the pond is. This is not a reason for discouragement. It is, if anything, a testament to how much science has accomplished, that we have been able to establish the existence and approximate proportions of things we cannot directly detect using nothing but light and careful reasoning. But it does underscore how much remains to be understood. Let us take a moment here to gently revisit the ground we have covered so far in this exploration, because we have traveled through several important ideas, and it is useful to hold them together before moving forward. We began with Hubble's discovery that the universe is expanding, a finding that transformed cosmology in the 1920s and established the framework within which everything else is understood. We then moved to the 1998 supernova observations, where two independent teams found that the expansion was not slowing down as expected, but was actually accelerating. We looked at how type 1 as supernovae function as reliable distance markers, and why the observations based on them are trustworthy. We explored the cosmological constant, Einstein's modified term, and how it provides the simplest mathematical description of dark energy as the energy of empty space. We considered how dark energy overpowers gravity, not through any special strength, but through its uniformity and constancy as matter becomes more dilute across the expanding cosmos. And we have now placed dark energy within the full energy budget of the universe, where it accounts for 68% of all that exists. With this foundation in place, we are ready to move deeper into the nature of dark energy itself. In the chapters ahead, we will explore how dark energy relates to and differs from dark matter, why the theoretical prediction for dark energy's value is so wildly at odds with what we observe, what alternative theories have been proposed to explain the acceleration, and how modern scientific instruments are attempting to pin down dark energy's properties with greater precision. We will also look at what an accelerating universe means for the very long-term future of everything. Each of these threads is worth following carefully and slowly. There is no need to rush. The ideas are subtle, and they deserve time to settle. One of the most common sources of confusion when people first encounter cosmology is the relationship between dark energy and dark matter. The names sound similar. Both contain the word dark. Both refer to things we cannot see. Both are fundamental to the current model of the universe, and yet they are completely different phenomena, with different properties, different behaviors, and different roles in the story of how the cosmos came to look the way it does. The confusion is understandable, and it is worth addressing carefully, because keeping the two concepts clearly separate makes everything else in this subject considerably easier to follow. Let us start with what they have in common, because there are genuine similarities, and acknowledging them honestly helps clarify where the differences lie. Both dark matter and dark energy are invisible. Neither interacts with light in any way that allows direct detection. Both were inferred through their effects on things we can observe, rather than through any direct measurement. Both are components of the universe's energy budget, whose fundamental nature remains unknown. And both were named using the word dark specifically because of that invisibility, that absence of any interaction with the electromagnetic spectrum. That is where the similarities end. Dark matter behaves, in most respects, like ordinary matter. It has mass. It is subject to gravity and responds to gravity the way ordinary matter does. It clumps together under gravitational attraction. It forms structures. Over billions of years, dark matter gathered into enormous halos and filaments, and those structures became the scaffolding within which galaxies formed. The ordinary matter we can see, the gas and dust and stars, accumulated within the gravitational wells created by dark matter. Without dark matter, galaxies as we know them would not exist, because ordinary matter alone would not have had enough gravitational pull to assemble into the structures we observe. Dark matter, in other words, promotes structure. It draws things together. It is additive to gravity in its effects. Where dark matter is concentrated, gravity is stronger, things fall inward, and structure grows. Dark energy does essentially the opposite. It does not clump. It does not respond to gravity in the way matter does. It is spread uniformly across all of space, at the same density in every cubic meter regardless of what else is nearby. It does not gather around galaxies or concentrate in any region of space. Its distribution is completely smooth and homogeneous, and its effect on the universe is not to draw things together, but to drive them apart. It works against the formation of structure at the larger scales, not by actively pushing things away in the way a force pushes a physical object, but by causing the space between unbound structures to expand faster and faster, making it progressively harder for gravity to bridge the growing distances. Another key difference lies in how each component behaves as the universe expands. When the universe expands, the density of matter, both ordinary and dark, decreases. Spread the same amount of matter over a larger volume, and the density goes down. This is intuitive. Dark matter follows this same pattern. its density diluting as space grows. Dark energy, at least in its simplest form as a cosmological constant, does not dilute at all. Its density stays exactly the same as the universe expands. New space carries the same energy density as old space. This is the property that makes dark energy so unusual and so consequential. It is what allows dark energy to eventually dominate over matter, because matter dilutes while dark energy does not. There is also a difference in when each became important in the universe's history. Dark matter was crucial from very early on. In the first hundreds of thousands of years after the Big Bang, dark matter was already forming the seeds of the large-scale structure that would later organize galaxies and galaxy clusters. Its gravitational influence shaped the young universe profoundly. Dark energy, by contrast, was irrelevant in the early universe. When everything was packed densely together, the constant energy density of dark energy was utterly negligible compared to the enormous densities of matter and radiation. It only became significant as the universe expanded and matter became dilute enough for dark energy's constant contribution to matter in relative terms. A simple way to hold the distinction is this. Dark matter is a substance that has mass and gravitational attraction and exists in certain places more than others. Dark energy is a property of space itself, present everywhere equally, with no mass and no gravitational attraction in the conventional sense, but with an influence on the expansion of space that becomes dominant when matter is sufficiently dilute. They are both dark, in the sense of being invisible and unknown, but they are as different from each other as water is from temperature. One is a thing, the other is a condition. One clumps and organizes, the other is smooth and expansive. One helped build the universe we see, the other is gradually pulling it apart. Understanding this distinction clearly is important, because the two concepts often appear together in discussions of cosmology, and conflating them leads to confusion about what each one does and why each one matters. In the previous video in this series, we explored dark matter in depth, tracing its role in galaxy formation, gravitational lensing, and the large-scale structure of the cosmos. In this video, dark energy is our subject, and keeping the two cleanly separated in mind will help as we move into the more theoretical territory ahead. With the distinction established, we can now turn to one of the most striking and troubling aspects of dark energy as a concept. We have a mathematical description of it that works extremely well. We have a name for it. We have a good measurement of how much of it there is. But when physicists try to calculate what it should be from first principles, using the best theories available, the answer they get is so wildly different from what we observe that it represents perhaps the most severe failure of theoretical prediction in the history of physics. This problem is important enough to deserve its own careful exploration. There is a habit in popular science of presenting physics as a discipline that has things largely figured out, with a few interesting puzzles remaining at the edges. The reality is more complicated. Physics contains some genuinely deep tensions, places where two well-tested and highly successful theories produce answers that cannot both be right, and where no one yet knows how to resolve the conflict. The cosmological constant problem is one of the most dramatic examples of this kind of tension, and understanding it helps convey both how serious the mystery of dark energy is and how much work remains to be done. To appreciate the problem, we need to bring together two of the most successful theories in the history of physics: general relativity and quantum field theory. General relativity, as we have discussed, is Einstein's theory of gravity and spacetime. It describes how mass and energy curve the fabric of space-time, and how that curvature governs the motion of objects and the large-scale behavior of the universe. It has been tested to extraordinary precision in countless experiments and observations. The predictions of general relativity have been confirmed again and again, from the bending of light around the sun, to the behavior of binary pulsars, to the recent direct detection of gravitational waves. It is one of the most precisely verified theories in science. Quantum field theory is the framework that describes the behavior of particles and forces at the smallest scales. It underlies the standard model of particle physics, which accounts for the electromagnetic force, the weak nuclear force, and the strong nuclear force, along with all the known elementary particles. Quantum field theory has also been tested to extraordinary precision. Its predictions for certain physical quantities, such as the magnetic moment of the electron, agree with experimental measurements to more than 10 significant figures. It is, by some measures, the most accurately tested theory in the history of science. These two theories are the twin pillars of modern physics. Between them, they describe virtually everything we can observe, from the behavior of quarks inside atomic nuclei to the motion of galaxies across the cosmos. And when it comes to dark energy and the cosmological constant, they are in catastrophic disagreement. Here is the issue. Quantum field theory predicts that empty space is not truly empty. The vacuum, meaning the lowest energy state of a quantum field, is not a state of zero energy. It is filled with fluctuations, with pairs of particles and antiparticles that briefly come into existence and annihilate, with the baseline energy of fields that permeate all of space. This vacuum energy is a genuine prediction of quantum mechanics, not a hypothetical artifact. It has measurable consequences. The Casimir effect, an experimentally confirmed phenomenon, where two uncharged metal plates placed very close together experience an attractive force due to vacuum fluctuations, is direct evidence that vacuum energy is real. The question is, how much vacuum energy is there? When physicists calculate the expected vacuum energy density using the principles of quantum field theory, they need to add up the contributions from all the quantum fields that exist. The calculation depends on what assumptions you make about the energy scales involved. But even with conservative assumptions, the predicted vacuum energy density comes out to be enormously larger than the observed value of the cosmological constant. How much larger? The discrepancy is typically estimated at around 10, raised to the power of 120. That is a 1 followed by 120 zeros. The theoretical prediction exceeds the observed value by a factor that is essentially incomprehensible in everyday terms. This is not a small discrepancy that might be resolved by a refinement in the calculation. It is the largest mismatch between theory and observation ever encountered in physics. There is a related but slightly different version of the problem that is also worth noting. Even if you could somehow explain why the vacuum energy is as small as it is observed to be, a separate puzzle remains. Why is it the particular value it is? The observed value of the cosmological constant is small, but it is not zero. If some unknown mechanism were cancelling out the vacuum energy, why would it cancel almost all of it, but leave behind this tiny residual? There is no obvious reason why the cancellation should be so nearly perfect, but not quite complete. This second aspect of the problem is sometimes called the coincidence problem. We happen to live at a time when the density of dark energy and the density of matter are within roughly the same order of magnitude. A few billion years ago, matter dominated strongly. A few billion years from now, dark energy will dominate even more overwhelmingly. The fact that we live at the precise epoch when the transition between the two is occurring, and when the densities of the two are roughly comparable, strikes some physicists as unlikely if there is no deeper reason for it. Of course, there is a possible anthropic response to this. Intelligent observers who can ask such questions might only arise during a certain window of cosmic history, when conditions were right for stars and planets and chemistry. But this kind of reasoning is philosophically contested and does not constitute a physical explanation. The cosmological constant problem has been known since the 1960s and 1970s, when physicists first began seriously calculating the expected vacuum energy. Despite decades of effort, no convincing solution has been found. Many approaches have been tried. Supersymmetry, a theoretical framework that extends the standard model by pairing each particle with a partner of different spin, was once hoped to resolve the problem by causing the vacuum energy contributions of particles and their partners to cancel. But supersymmetry, even if it exists, turns out to reduce the discrepancy by only a limited amount, and no evidence for supersymmetric particles has been found at current accelerators. String theory, the candidate theory for a unified description of all forces including gravity, has its own approach to the problem through what is called the string theory landscape, an enormous number of possible vacuum states, each with different physical properties. The idea is that our universe happens to occupy one of the rare vacua with a small cosmological constant, but this approach is difficult to test and relies on concepts that remain speculative. Other approaches include modifications to general relativity at large scales, theories in which the cosmological constant is not a fixed quantity, but a dynamical field that evolves over time, and various attempts to find symmetry principles that would naturally predict a small but non-zero vacuum energy. None of these have yet provided a fully satisfying resolution. The honest position, the one that most physicists would acknowledge, is that we do not know why the cosmological constant has the value it does. We have measured it carefully. We know it is there. We know its effects. But the theoretical understanding of why space should have this particular energy density, rather than a vastly larger one or precisely zero, remains entirely absent. It is one of the most profound open questions in fundamental physics, and it sits at the heart of our ignorance about dark energy. The cosmological constant is the simplest explanation for dark energy, and it fits the current observational data well. But simplicity and fit are not the same as correctness, and the deep theoretical difficulties surrounding the cosmological constant have motivated physicists to explore whether dark energy might be something more complex and more dynamic than a fixed property of the vacuum. These alternative theories do not yet have the observational support needed to displace the cosmological constant as the preferred explanation, but they represent serious scientific inquiry, and exploring them illuminates the range of possibilities that remain open. They also help clarify what future observations might be able to tell us, because different theories of dark energy make slightly different predictions for how the universe should expand over time, and sufficiently precise measurements might eventually distinguish between them. The most studied alternative to the cosmological constant is called quintessence. The name comes from the classical Greek concept of a fifth element, the mysterious substance that filled the heavens beyond the four earthly elements of earth, water, fire, and air. In modern cosmological usage, quintessence refers to a hypothetical scalar field, a type of quantum field that has a value at every point in space, that permeates the universe and carries energy. Unlike the cosmological constant, which is fixed and unchanging, a quintessence field can evolve over time. Its energy density can change as the universe expands, and the rate at which it changes depends on the shape of what physicists call the field's potential, a mathematical description of how the field's energy varies with its value. Different potential shapes lead to different behaviors of the quintessence field over time, and therefore to different histories of the universe's expansion. One of the appealing features of quintessence is that it offers a possible route to addressing the coincidence problem. Some quintessence models have what are called tracking solutions, where the field naturally evolves toward a state in which its energy density is comparable to the matter density over a wide range of cosmic epochs. This would make the current near equality of dark energy and matter density less of a coincidence and more of a consequence of the field's dynamics. Whether this actually solves the coincidence problem or simply relocates it to a different set of assumptions is a matter of ongoing debate. Quintessence fields are characterized by a parameter called the equation of state, usually written as the letter W, which describes the relationship between the field's pressure and its energy density. For a cosmological constant, W is exactly -1. This is a fixed value that does not change with time. For quintessence, W is also negative, meaning the field has negative pressure, which is what drives accelerated expansion, but its value can differ from -1 and can change over time. Observational constraints on W and on whether W varies with time are therefore a key target for dark energy surveys. If future measurements find that W is significantly different from -1, or that it is evolving, this would be strong evidence against the cosmological constant and in favor of a dynamical dark energy like quintessence. Another class of alternatives involves modifying general relativity itself, rather than adding a new field. In these theories, the accelerated expansion is not caused by an additional energy component at all. Instead, it arises because gravity behaves differently on the largest cosmological scales than Einstein's theory predicts. Modified gravity theories come in many variants, with names like FR gravity, scalar tensor theories, and massive gravity, each of which changes the equations of general relativity in specific ways. Some of these modifications can produce accelerated expansion without invoking dark energy as a separate component. Modified gravity theories are interesting partly because they are testable. General relativity makes precise predictions not just for the expansion history of the universe, but for how matter clusters and forms structures. Modified gravity theories generally predict different clustering behaviors, and comparing observations of large-scale structure to these predictions is one way to constrain or rule out specific modifications. Current observations are consistent with general relativity and place tight limits on how much it can be modified, but they do not yet definitively rule out all alternatives. There are also more exotic proposals. Some theories invoke extra spatial dimensions beyond the three we experience, suggesting that gravity leaks into these extra dimensions on large scales in ways that could affect cosmic expansion. Others propose that dark energy is not a smooth background, but is somehow coupled to dark matter, with the two interacting in ways that modify the expansion history. Still others suggest that the apparent acceleration might be an artifact of our location in the universe, specifically that we might be living near the center of a large underdense region whose local expansion rate differs from the cosmic average, though this possibility has been largely constrained by observations. Each of these proposals has theoretical motivations and faces observational constraints. None has yet emerged as a clearly superior alternative to the cosmological constant. The current data are consistent with a cosmological constant, meaning a fixed W equal to -1 with no time variation. But the data are not yet precise enough to rule out small deviations from this, and it is precisely those small deviations that current and future surveys are designed to measure. It is worth appreciating what this situation means for the practice of science. We have a model that works, the cosmological constant, and we have reasons to be uncertain about whether it is the final answer. Good science in this situation means continuing to test the model more precisely, taking the alternatives seriously, designing observations that could distinguish between them, and remaining genuinely open to being surprised. The history of cosmology over the past century suggests that surprises are not rare. The expansion of the universe was a surprise. The accelerating expansion was a surprise. It would be unwise to assume that the next major discovery is not waiting somewhere in the data we have not yet gathered. The discovery of dark energy in 1998 was made with a relatively small number of supernovae observed by two dedicated teams. The sample was large enough to establish the acceleration beyond reasonable doubt, but it was not large enough to say much about the detailed properties of dark energy, whether its density is truly constant, whether its equation of state is precisely -1, or whether it has changed over the history of the universe. Answering those questions requires far more data, gathered across a wider range of cosmic distances and with greater precision than was possible in the 1990s. In the decades since the original discovery, an enormous amount of scientific effort and engineering ingenuity has gone into building the instruments needed to measure dark energy more precisely. These instruments approach the problem from several different angles, using different physical phenomena as their measuring tools. The convergence of multiple independent methods, each with its own sources of uncertainty, is what gives cosmologists confidence in the overall picture. Supernovae surveys remain one of the primary tools. Modern surveys observe far larger numbers of Type 1 as supernovae than the original teams did, spread across a much wider range of redshifts, and therefore across a much wider range of cosmic history. The Dark Energy Survey, which operated from 2013 to 2019, using a purpose-built camera on a telescope in Chile, catalogued thousands of supernovae and used them to constrain the properties of dark energy with considerably greater precision than had previously been possible. Future surveys will go further still, with the Vera C. Rubin Observatory in Chile, now beginning full operations, expected to discover hundreds of thousands of supernovae over its decade-long survey. A second major tool is baryon acoustic oscillations, often abbreviated as BAO. This technique exploits a feature of the early universe that left a characteristic imprint on the large-scale distribution of galaxies we observe today. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma of matter and radiation. Sound waves propagated through this plasma, driven by the pressure of radiation pushing outward against the gravitational pull of matter. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, roughly 380,000 years after the Big Bang, the radiation decoupled from matter and streamed freely away. This decoupling froze the sound waves in place, leaving a characteristic scale imprinted in the distribution of matter. That scale, roughly 500 million light-years in today's universe, appears as a subtle preferred separation between pairs of galaxies. It acts as a standard ruler in much the same way that supernovae act as standard candles. By measuring this preferred separation at different redshifts, astronomers can trace how the universe's expansion has changed over time, which in turn constrains the properties of dark energy. The Dark Energy Spectroscopic Instrument, known as DESI, is currently the most powerful instrument dedicated to measuring baryon acoustic oscillations. Located at the Kitt Peak National Observatory in Arizona, DSE can measure the spectra of 5,000 galaxies simultaneously, using an array of fiber optic cables that can be precisely repositioned to target different objects. Over its planned 5-year survey, it will measure the positions of tens of millions of galaxies across a large fraction of the observable universe, producing the most detailed map of large-scale structure ever assembled. In early 2025, the DESI collaboration released results from its first full year of data. These results were notable for a specific reason. When the baryon acoustic oscillation measurements were combined with other cosmological data sets, including supernova observations and measurements of the cosmic microwave background, the combined analysis showed a mild but intriguing preference for a dark energy that is not perfectly constant. The data suggested that W, the equation of state parameter, might be slightly different from -1 and might be evolving over time. The statistical significance of this result was not yet at the level required to claim a definitive discovery, but it was sufficient to attract considerable attention from the cosmological community. If confirmed by future data, evolving dark energy would be a major development. It would rule out the cosmological constant as the explanation for acceleration and point toward a dynamical dark energy such as quintessence. It would also have implications for the ultimate fate of the universe, since a changing dark energy is not constrained to remain repulsive forever. Some models of evolving dark energy predict that the dark energy density could eventually decrease, slowing the acceleration, or even reverse sign, allowing gravity to eventually recollapse the universe. A third approach to measuring dark energy comes from weak gravitational lensing. Light from distant galaxies is deflected as it passes through the gravitational fields of intervening matter. This deflection causes the shapes of distant galaxies to appear slightly distorted, stretched in directions that reflect the distribution of matter between the galaxy and the observer. By measuring these distortions statistically across millions of galaxies, astronomers can map the distribution of matter in the universe and compare it to the predictions of different cosmological models. Dark energy affects not just the expansion history, but also how matter clumps and forms structure, and weak lensing is sensitive to both effects. The Euclid Space Telescope, launched by the European Space Agency in 2023, is designed specifically to measure both baryon acoustic oscillations and weak gravitational lensing across an enormous volume of the universe. Its survey will cover roughly 1/3 of the entire sky and extend to redshifts of about 2, meaning it will observe galaxies as they were when the universe was roughly 3 billion years old. The combination of its BAO and weak lensing measurements will constrain the properties of dark energy with a precision that is expected to be significantly better than anything currently available. The Nancy Grace Roman Space Telescope, developed by NASA and expected to launch in the mid-2000s, will complement Euclid's measurements with its own surveys of supernovae and weak lensing, extending the constraints on dark energy to higher redshifts and providing an independent cross-check of the results. Together, these instruments represent an unprecedented investment in understanding dark energy. The scientific community is genuinely uncertain what they will find. The most likely outcome, based on current data, is that they will confirm the cosmological constant picture with higher precision. But the DESI hints of evolving dark energy have introduced genuine uncertainty and the possibility that dark energy is more complex than a simple constant is being taken seriously. There is also the matter of the Hubble tension, a discrepancy that has grown in prominence over the past decade and that may or may not be related to dark energy. The Hubble tension refers to a disagreement between two different ways of measuring the current expansion rate of the universe, known as the Hubble constant. One method, based on observations of the early universe through the cosmic microwave background, gives a somewhat lower value. The other method, based on direct observations of relatively nearby supernova and other distance indicators, gives a consistently higher value. The two measurements have been refined and cross-checked extensively, and the discrepancy has not gone away. It currently stands at a level of statistical significance that is difficult to dismiss as a simple measurement error. Whether the Hubble tension reflects new physics, perhaps a form of dark energy that behaves differently in the early universe than in the late universe, or whether it reflects some systematic error in one or both measurements that has not yet been identified, is not yet known. It is one of the more actively debated questions in current cosmology, and resolving it may require either new observations or new theoretical ideas, possibly both. What all of this conveys is that the measurement of dark energy is an active and ongoing enterprise. The picture established in 1998 has been confirmed and refined many times over, but the finer details of dark energy's properties remain genuinely uncertain, and the next generation of surveys is expected to sharpen those constraints considerably. Whether they will reveal a simple cosmological constant or something more complex and dynamic is one of the most anticipated questions in contemporary astrophysics. One of the most natural questions that arises when contemplating dark energy is what it means for the future. If the universe is accelerating, if the expansion is speeding up rather than slowing down, then what happens next? Where does this lead? Not in the near term, but in the deep future, across timescales so vast that they dwarf anything in human experience. The answer depends significantly on the nature of dark energy, and since we do not fully understand dark energy, our picture of the universe's ultimate fate is correspondingly uncertain. But we can trace the major possibilities carefully and consider what each would mean for the cosmos over the very long run. The simplest scenario, and the one most consistent with current data, is that dark energy is a true cosmological constant, with a fixed energy density that does not change over time. In this case, the accelerating expansion continues indefinitely. Galaxies that are not gravitationally bound to each other move apart faster and faster. The space between galaxy clusters grows at an ever-increasing rate. Over tens of billions of years, distant galaxies recede beyond what will become a permanent horizon, the boundary beyond which light can never reach us regardless of how long we wait, because the space between us and those galaxies is expanding faster than light can cross it. This is not a violation of relativity. Light still travels at the same speed through local space, but the expansion of space itself is not constrained to move slower than light. When the expansion rate across a large enough distance exceeds the speed of light, objects on either side of that distance become causally disconnected. No signal can ever pass between them. They are permanently separated, not by distance in the conventional sense, but by the ongoing stretching of the space between them. Over time, in this scenario, the observable universe as experienced by any future civilization would shrink. Galaxies beyond our local group would eventually recede beyond the horizon and disappear from view, not because they stop existing, but because their light can no longer reach us. The Milky Way and its gravitationally bound neighbors would remain, but everything else would fade from observability. A civilization billions of years in the future, if such a thing existed, would look out into space and see far less than we do today. They might conclude, based on what they could observe, that the universe consisted only of a small cluster of galaxies surrounded by emptiness, they would be wrong in the sense that vast numbers of galaxies would still exist beyond their horizon, but they would have no way of knowing it. On even longer timescales, the stars in galaxies burn through their fuel and die. New star formation gradually slows as the gas reservoirs that feed it are depleted. The last stars flicker out after perhaps 100 trillion years. What remains are cold stellar remnants, black holes, and an expanding, cooling, darkening cosmos. This endpoint is often called the heat death of the universe, a state of maximum entropy in which no thermodynamic work can be extracted, no ordered structures can form, and no process of any kind can occur. It is not a dramatic end. It is more like a gradual dimming, a universe running down to its lowest possible energy state and staying there. This scenario, the cosmological constant leading to eternal accelerating expansion and eventual heat death, is sometimes called the Big Freeze. It is the most commonly discussed long-term fate in current cosmological thinking, and it is the one most consistent with present observations. But it is not the only possibility. If dark energy is not a fixed cosmological constant, but instead a dynamical field like quintessence, other fates become possible. If the energy density of dark energy increases over time rather than remaining constant, the acceleration of expansion would itself accelerate, growing faster and faster without limit. In this scenario, eventually the expansion rate becomes so extreme that even gravitationally bound structures begin to be torn apart. Galaxy clusters would be ripped apart first, then individual galaxies, then solar systems, then planets, and eventually even atoms themselves would be unable to hold together against the accelerating expansion of the space within them. This scenario is called the Big Rip, and it would occur at a finite time in the future if the equation of state parameter W is less than -1, a condition sometimes called phantom dark energy. Current observational constraints on W do not rule out phantom dark energy entirely, though they suggest it is not strongly favored. The DESI results hinting at evolving dark energy have renewed interest in this possibility, though the data are not yet precise enough to determine whether W crosses below -1. If future surveys confirm phantom dark energy, the Big Rip would become a serious candidate for the universe's fate, occurring perhaps tens of billions of years from now. If, on the other hand, dark energy is a dynamical field whose energy density decreases over time rather than increasing, the acceleration of expansion could eventually slow, stop, and even reverse. In this case, gravity could regain dominance over the large-scale dynamics of the universe, and the expansion could eventually turn into contraction. The universe would then collapse inward, with matter and energy falling together in what is called the Big Crunch, a reversal of the Big Bang. Recent work from the Yonsei University team, published in late 2025, suggested on the basis of corrected supernova data that the universe may already be entering a phase of deceleration, which would be consistent with a dark energy that is weakening over time. This result has been met with both interest and skepticism from the broader community, and confirmation will require additional independent evidence. There is also a more exotic possibility, sometimes called the Big Bounce, in which a collapsing universe does not simply end, but instead reaches a minimum size and bounces back into a new expansion. Some theories of quantum gravity predict that the singular endpoint of a collapse is avoided by quantum effects, leading to a new cycle of expansion. Whether anything from the previous cycle would survive or be observable in the new one is deeply uncertain. It is worth sitting with these possibilities not as sources of anxiety, but as a form of perspective. The timescales involved are incomprehensibly vast. The heat death of the universe, if that is indeed the endpoint, lies so far in the future that the current age of the universe would be an imperceptibly small fraction of the time remaining. The universe has barely begun by these measures. The stars are still young. The structures that exist today are still forming and evolving. Whatever the ultimate fate, it is separated from the present by an expanse of time that has no meaningful analogy in human experience. There is something calming in this, if you allow it to be. The universe is patient. It unfolds at its own pace, across timescales that render our concerns about the future almost irrelevant in cosmic terms. And the fact that we can sit here, on a small planet around an ordinary star in a middle-aged galaxy, and trace the possible futures of the entire cosmos using nothing but light and mathematics, is itself a remarkable feature of the universe we inhabit. We have traveled a considerable distance through the subject of dark energy, from its discovery through supernovae observations to the cosmological constant and its theoretical problems, from the behavior of dark energy at different cosmic scales to the instruments currently working to understand it better, and through the range of possible futures it might deliver. It is worth pausing here to take stock of what we genuinely do not know, not as a list of failures, but as an honest account of where science currently stands. The most fundamental unknown is the simplest to state and the hardest to resolve. What is dark energy? We have a mathematical description that fits the observations well. The cosmological constant, a fixed energy density associated with the vacuum of space. But a mathematical description is not the same as a physical understanding. We do not know what gives rise to the vacuum energy. We do not know why it has the value it does, rather than being either vastly larger, as quantum field theory predicts, or exactly zero, as some symmetry principle might suggest. The gap between the predicted and observed values of vacuum energy remains the largest unexplained discrepancy in physics. We do not know whether dark energy is truly constant or whether it evolves. The cosmological constant model assumes it is fixed, and current data are broadly consistent with this. But the hints from DESI and from other recent analyses suggest the possibility of evolution, and this question will not be definitively answered until the next generation of surveys provide substantially more precise measurements. Until then, we are working with a model that fits current data, without being able to confirm whether it is the final picture or an approximation to something more complex. We do not know whether dark energy is the same everywhere. The cosmological constant, by definition, is uniform across all of space. But if dark energy is a dynamical field, rather than a constant, it might vary from place to place, as well as changing over time. Current observations are not yet sensitive enough to detect spatial variations in dark energy, and testing for them requires surveys that map the universe's structure with enough resolution and depth to look for such effects. We do not fully understand the Hubble tension. The disagreement between early universe and late universe measurements of the expansion rate is real and persistent, and it may point to new physics that our current models do not capture. Whether this new physics involves dark energy, dark matter, the physics of the early universe, or some measurement systematics that have not yet been identified, remains an open question. The tension has been with us for long enough that a simple measurement error becomes less plausible as an explanation, though it cannot yet be ruled out. We do not have a fundamental theory that explains why the cosmological constant has the value it does. This is the cosmological constant problem discussed in an earlier chapter, and it remains entirely unresolved despite decades of effort by some of the most capable theoretical physicists in the world. String theory, supersymmetry, and various other approaches have been explored, and none has produced a satisfying answer. The value of the cosmological constant appears to be a brute fact about our universe, with no deeper explanation yet in sight. We do not know whether dark energy will remain as it is, or whether it will change in ways that affect the universe's future. If it is truly a cosmological constant, it will persist unchanged forever, and the universe's future is the long, slow cooling described in the previous chapter. If it evolves, the future could be quite different. The range of possibilities, from eternal expansion to big rip to eventual collapse, reflects our genuine uncertainty about what dark energy is and how it will behave over cosmic time. Let us take a moment here to gently revisit the journey of this exploration as we approach its final stages. We began with the expanding universe and traced the path from Hubble's observations to the supernova teams of the 1990s. We explored how Type 1a supernovae function as cosmic rulers and how their measurements revealed an accelerating expansion that no one had anticipated. We looked at the cosmological constant, its history with Einstein, its abandonment and restoration, and its role as the simplest description of dark energy. We considered how dark energy overpowers gravity at cosmic scales without affecting anything at smaller scales, and placed dark energy within the full energy budget of a universe that is 95% unknown to us. We distinguished dark energy from dark matter, explored the theoretical problem posed by the cosmological constant, considered the range of alternative theories that might explain the acceleration, and surveyed the instruments currently working to sharpen our understanding. We traced the long-term futures that different models of dark energy imply, from heat death to big rip to eventual collapse. What remains as we move into the final chapters is reflection, a consideration of what it means to live in a universe dominated by something we do not understand, and what that says about the nature of knowledge and the ongoing practice of science. There is a particular kind of wonder that comes not from certainty, but from the awareness of how much remains open. Science is often presented as a process of closing questions, of replacing mystery with explanation, of moving steadily from ignorance toward knowledge. And this is true in important ways. Over the past century, we have learned an extraordinary amount about the universe, far more than any previous generation of humans could have imagined. And yet dark energy reminds us that the deepest questions are still open. The dominant component of the universe, the thing that makes up 68% of everything that exists, the force that is shaping the long-term fate of all structure and all matter and all light, is something we do not understand at a fundamental level. We have measured it. We have named it. We have described its behavior with mathematics, but we cannot say what it is. This is not a failure of science. It is science working exactly as it should, pushing to the edges of what is known and finding that the edges are still far from any final understanding. Every era of science has lived with deep unknowns alongside its achievements. Newton explained the motion of the planets, but could not say what gravity was or how it acted at a distance. Maxwell unified electricity and magnetism, but could not explain what the electromagnetic field was made of. The architects of quantum mechanics built one of the most precise and useful theories in history while disagreeing fundamentally about what it means. Dark energy belongs to this tradition of productive mystery. It is a thing we have found and cannot fully explain, and the search for an explanation is generating some of the most interesting physics and astronomy of our time. The instruments being built to study it, Darcy, Euclid, the Vera Rubin Observatory, the Roman Space Telescope, are among the most sophisticated scientific instruments ever constructed. The theoretical frameworks being explored in response to it are pushing the boundaries of quantum gravity, string theory, and cosmology. The mystery is not standing still. It is being actively pursued from many angles with extraordinary tools. At the same time, there is something worth appreciating in the scale of what we have already established. The universe is 13.8 billion years old and expanding in every direction. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars. It is pervaded by invisible dark matter whose gravity shaped every structure we can see, and by dark energy whose pressure is stretching the space between those structures at an accelerating rate. We exist on a small rocky planet in the outer arms of a middling galaxy, and from this vantage point, using instruments we have built over just a few centuries of organized science, we have traced the history and energy budget of the entire observable cosmos. The light that reaches our telescopes carries information from billions of years ago, from objects so distant that the space between us and them has expanded enormously since the light began its journey. We read that information. We extract from it the expansion history of the universe. We infer the presence of dark energy. We constrain its properties to within a few %, and we do all of this without leaving the surface of our planet. This is a genuinely remarkable achievement of human intelligence and curiosity. Dark energy, in this light, is not so much a problem as a frontier, a place where our current knowledge ends and genuine uncertainty begins. Frontiers are not comfortable places. They are places where the usual tools are not quite sufficient and where new ideas are needed. But they are also the most interesting places to be, the places where the next great discovery is waiting. We do not know what dark energy is. We do not know why the cosmological constant has the value it does. We do not know whether the universe's expansion will continue forever or eventually reverse. These are not embarrassing gaps in our knowledge. They are the honest acknowledgement that the universe is larger, stranger, and more interesting than any model we have yet constructed to describe it. The universe has been expanding for nearly 14 billion years. It will continue expanding, at least for the foreseeable future, driven by a force we can measure but cannot fully explain. The galaxies are drifting apart, slowly and steadily, carried by the stretching of the space between them. The stars are burning, as they have been for billions of years, their light crossing the expanding void. And here, on this small and temporary platform, we look out at all of it and try to understand. There is something deeply fitting about ending a long exploration of dark energy with an acknowledgement of how much remains unknown. The subject itself is an unknown. It invites not conclusions but questions, not certainty but wonder. And wonder, when held gently, without the need for immediate resolution, is one of the most restful states the mind can occupy. The universe is not in a hurry, neither are we.